Today we are going to talk about how to improve player balancing in games using a novel technique for modeling players' aiming ability. We will start by talking about aiming in games and how to balance for people's differences in aiming ability. We will explain how these balancing algorithms require us to know how good individual players are at aiming tasks, and we will then introduce our new model and report on a study showing that it is accurate and fast to train. Gaming is an important social activity for many people, but players vary in gaming ability, and lower ability may result in reduced enjoyment or even exclusion from social gaming. This can be especially difficult for people with fine motor deficits that make gaming harder. One ability that affects many games is aiming. Some brief examples include Apex Legends, where players aim and shoot at enemies, Asteroids, where players aim their ship to shoot at moving asteroids, Subway Surfers, where players aim their avatar to avoid obstacles and collect coins, and Mario Run, where players aim Mario to jump on platforms and enemies and collect coins. Differences in aiming ability can make it hard for people to play together. One outcome of our research is confirmation that aiming has both spatial and temporal components. For example, in this jellyfish fighting game, players must point their fist in the correct direction and time a punch to hit at the right time. For example, if Lefty wishes to punch Dexter, then Lefty needs to point their fist at Dexter, spatial aiming. However, this is not enough. If Lefty punches before Dexter is in range, Lefty has punched too early. When Lefty is close enough, this is the correct time to punch. If Lefty punches too late, Dexter has already swum past and the punch will miss. One way to address differences in aiming ability is to use aim assistance, in which the game helps players aim at targets. For example, sticky targets in Fortnite cause the aiming reticle to stick to the target when it gets close, making it easier to aim. However, different players will require different amounts of assistance. This is called personalization. Dynamic difficulty adjustment attempts to determine the amount of assistance required during gameplay. However, this has proved difficult for aiming because it is difficult to measure how much personalization is required. To understand how much assistance someone needs, we must understand what makes aiming difficult. We have found experimentally that the difficulty of an aiming task can be captured by 4 parameters, 2 for spatial aiming and 2 for temporal aiming. The difficulty of spatial aiming can be described by the size and speed of the target. For example, in Skyfighters 3D, a more distant plane is smaller and more difficult to hit, and a fast plane is harder to hit than a slow one. For temporal aiming, performing an action at the right time, there are another 2 difficulty parameters. The first is how much time the player has to anticipate and set up the aiming action. For example, in the baseball game MLB The Show, the batter will see the pitcher throw, giving a warning that the ball is on its way. This warning time is called cue viewing time. A longer cue viewing time will make it easier for the batter to anticipate when to swing. Also, the batter must hit the ball as it goes over the plate. A slower ball will spend more time over the plate, making it easier to time the swing. This time interval, where a swing will result in a hit, is called the temporal width. As shown in the paper, people differ significantly in their ability to perform spatial and temporal aiming. We also show that spatial and temporal difficulty are independent. Spatial parameters are poor predictors of temporal difficulty, and vice versa. See paper for details. To perform aim assistance, we can change difficulty of aiming at a target by modifying that target's parameters. For example, we can help with spatial aiming by making the target's hitbox larger, or by making the target slower. We can help with temporal aiming by increasing the cue viewing time. For example, by giving the pitcher a longer throwing animation. Or we can slow the ball as it passes over the plate to increase temporal width. To do this, we must know how much assistance to give each player. Some players need a little assistance, some need a lot, and some need none at all. If we give the wrong amount of assistance, we may make the game less balanced instead of more. To figure out how much assistance we give each person, we need to know how good the person is at aiming. To help with this, we have developed a new way of modeling individuals' aiming ability. Given a specific aiming task, as defined by the difficulty parameters, the model is able to predict how well the player will be able to aim at it. By altering the parameters and reapplying the model, designers can find a set of difficulty parameters that give the desired predicted performance for this particular player. The output of the model is predicted performance of a given player for a task with a given difficulty. This prediction takes the form of a distribution of hit locations in time and space. Players will not always hit the same place while aiming, or at the same time. The place or time they actually hit is called an endpoint. The spatial and temporal positions of these endpoints have a Gaussian distribution. Good aiming performance will have a mean near the center of the target, and a low standard deviation, indicating tight clustering. To characterize an individual's aiming ability, the model must be trained. Spatial and temporal aspects of the model are trained separately, with spatial difficulty determined by target's size and speed, and temporal difficulty determined by target's Q viewing time and temporal width. The model is trained by varying the difficulty parameters. For example, we train the spatial part of the model using cross of 3 target sizes and 3 target speeds. The player faces multiple targets in each session, in each condition, and their spatial and temporal endpoints are recorded. The mathematics behind the model draw from approaches by Huang et al. And Li et al. As detailed in the paper. We performed a study to determine the model's properties. We wanted to find out if the model's predictions are accurate enough to allow good personalization of player balancing algorithms, and if it could be trained quickly enough that it doesn't unreasonably delay the player from starting to play. We performed a 72-participant study on Amazon Mechanical Turk to evaluate the performance and training time of the model. For this study, we used a bespoke game called ChronoSwarm, where players try to click a spatial target while a moving clock hand is between 2 lines, forming the temporal target. The game is designed such that gameplay is entirely about spatial and temporal aiming, removing potential compounds such as strategy, quality of enemy AI, or luck. Here is a brief gameplay clip of a player playing ChronoSwarm trying to hit the spatial and temporal targets at the same time. In the study, the difficulty parameters varied between gameplay rounds. We had 3 values each of speed and width, resulting in 9 spatial conditions, and 3 values each of Q viewing time and temporal width, resulting in 9 temporal conditions. The set of conditions was iterated 30 times. These iterations were divided into training and test data. The test data set uses the last 10 iterations of each condition. To evaluate how much training data is needed, we trained 16 different versions of the model for each participant using variable quantities of training data, ranging from 5 to 20 iterations per condition. The predictions from these trained models were then tested by comparing to the test data. For the spatial results, this blue line shows that the average error across all participants. We can see there is little improvement in error as the amount of training data increases, suggesting that 5 data points per condition is sufficient to train the model. This gray line represents half the size of the smallest target, giving us a sense of how much error there is on average with the model. For temporal results, this purple line shows average error. There is some improvement in error as the amount of training data increases. However, we see that even at 5 data points per condition, the error is smaller than half the smallest temporal width. This suggests that initial training of the model requires only 90 observations, 5 per condition. This is short enough that, depending on the game, it may be trainable during gameplay, and if not, can be trained in a brief tutorial, 3 minutes for ChronoSwarm. A dynamic difficulty adjustment algorithm can then update the model with further observations during play. Our large goal in this research was to provide a fast and accurate method for determining individuals' aiming ability so that we can better support player balancing techniques that rely on personalizing an algorithm to a person's abilities. These results show that this goal has been met. Specifically, the model is accurate, the training is rapid enough to train in a tutorial and update dynamically. We have demonstrated the importance of both spatial and temporal aiming, and we have determined how the essential difficulty parameters interact with spatial and temporal aiming ability.